make a speech. Professor is from School of Mechanical Engineering and Automation, Harbin Institute of Technology, Shenzhen, China. His research has mostly involved flow induced vibration, flow induced noise, turbulent wind wind load on structures, ground structure interaction, hydrodynamics of swimming animals, flow control, and energy harvesting from wind and occasion current as well.
Thank you very much, Mr. Chairman, for the introducing me. I'm from Harbin Institute of Technology. Today I'll be talking about flow, heat transfer, and forces on cylinder from circular by square to circular. We can change the cross section of cylindrical structure from square to circular by changing the corner radius. Okay, this is the outline of my presentation. First, I will give a background, then simulation technique. The focus will be on results, on the effect of R over R on forces, flow, and heat transfer, and the effect of R over R and alpha, effect of R over R and Reynolds number. This is the Reynolds number like flow velocity, and finally conclusion. Okay, then let's see the first the background. You will see some here. Here you will see some like the CPU, mother, and some chips on board, like a capacitor, different components. These components may be circular, maybe square. You will find later. The important things is heat transfer is very important in this application. Like everybody has computer or laptop. You see, if your laptop is overheated, then it will shut down. Okay, that means some component in your computer is overheated. Okay, why it is overheated? Heat transfer is not enough. Cooling is not enough. Okay, like here you see we have dust. If you see at the bottom of your laptop, you will find the dust at the inlet. Okay, you need to clean, otherwise your computer laptop will be overheated. So like here, mother board, you'll see some of circular shape capacity and some of what is square shape. The general question: which shape is good for heat transfer, circular or square, or some random shape? We don't know. Then also you see the building structure. Some are twisted, some are rounded corner, some are like circular shape. Okay, you'll find. And there is a wind force on the buildings or structure. Then which shape has the smallest wind force on the structure? That's again a question. If you see, like a circular cylinder, we have basic understanding of flow. When you have flow and there is a circular cylinder, and if you change the Reynolds number, there will be different flow patterns. Like when the Reynolds number is very small, less than 5, then you will find creeping flow. There is no separation of the flow from the cylinder. And if you increase the Reynolds number slightly, then if like 5 to 48, you will find a steady separation. There is no Karman water seeding, but you will find steady separation there will be two recirculation bubble behind the cylinder. If you further increase the Reynolds number like 48 to 180, you will find alternative thermal vortex setting like this. Okay, this is fascinating. It is for thermal vortex setting. This alternative setting induce the fluctuating forces on the structure. And if you further increase the Reynolds number in this regime, then you will find transition in the weight transition of the lanyard. Like there will be transition in the weight. And at high Reynolds number like here, you will find the transition in the shear line. This is called the shear line. And this beyond this is the weight. So now the transition happens in the shear line. If we further increase the Reynolds number beyond this, then we will find a transition in the boundary. And the flow control technique. Flow control can enhance the heat transfer. It can reduce the wind loads, fluid forces on the surface. Okay, there are two ways, dominant techniques for controlling the flow or forces or heat transfer. One is the passive control, and another is the active control. Active control requires energy input. Okay, you need to give some energy input to actuate your actuators or something. But in the case of passive control, you don't need the input energy. Just put some control objects or change the shape. Okay, if you change the shape, this is an excellent technique to control the flow. Okay, or enhance the transfer. You are controlling the flow in a way. It is you are enhancing the heat transfer or reducing the forces. And geometry. Okay, geometry might be circular, might be square, might be shaped, might be flat. There are various geometry. Okay, and we can change the geometry by corner modification. Like we have the square cylinder, then we can round the corner, or we can convert the corner, or we can reset the. Okay, there are different ways of changing the shape corner. Our focus is rounded corner. Like if you see, for a square cross section, R over R is the corner radius. Okay, at the corner radius is 0. That means very sharp. Okay, if you change the R over R, it is the half width. Okay, half here, like the radius. Okay, the radius. If you change the R from 0 to 1, it will be the square cylinder will be modified to circular cylinder. Okay, if we increase the radius gradually, then it is modified to circular cylinder. Our goal is when we are changing the radius, corner radius from this to this, how the heat transfer changes. Okay, how the forces on the structure changes. So first key issue is changing the corner radius. We'll change the corner radius from square to circular cylinder. Okay, we'll modify it quickly. Then what is the optimum shape? I mean the output corresponding to maximum heat transfer or minimum force. Like which configuration has the maximum heat transfer or minimum force? We'll choose that configuration. Right? Then second key issue, change the incidence angle. You see, this is the square cylinder or rounded corner. It may be alpha equals 0 means this is alpha equals 0. If the flow is from left to right, then it will 0. We can change this orientation. Okay, then it may be something like this. This is the alpha with respect to the flow. Then if we change the flow, is there any variation in heat transfer or forces like this? The flow can flow maybe in this way, can flow maybe this way. Which flow is better? Okay, that's interesting issue. Then third key issue is the change in the Reynolds number. Reynolds number like fan velocity. Will it turn the fan velocity very high or low or which velocity? Okay. What is the correspondence between the Reynolds number in the flow velocity and the heat transfer and forces? So we did the simulation indeed here at low Reynolds number. Here the computational domain is simulation. We have the structure at the center of the computational domain. This is the upstream length, downstream length of the computational domain, and lateral width is 20 W. Here is the inlet, and here is the outlet flow. This is the mesh system around the cylinder. Just remember this is the extreme velocity, non-uniform extreme velocity. U star is U over U infinity. U infinity is the inlet velocity. Similarly, cross extreme velocity V star in the V star in the y direction, velocity in the y direction. This is the V over infinity in the same way. And normalized temperature is this one. T infinity is the inlet temperature, and TW is the wall temperature of the cylinder, like wall temperature of the capacitor. Okay. Then this is the normalized temperature. T is arbitrary temperature of the flow field. Okay. Reynolds number is defined in this way. If you are not familiar with the fluid mechanics, just consider the Reynolds number is like a flow velocity. We solve the quadratic equation like a neighbor equation and continuity equation. This is connected to the well-known heat transfer equation and Nusselt number that characterizes heat transfer from the cylinder. Then effect of R over R means that we're changing the corner radius. Then how it affects forces, flow, and heat transfer. We'll see here when we're changing from this to this. This is the first step. Okay, like velocity converts. This is R over R0 means E square cylinder. And this is R over R means circular cylinder. We're changing the corner radius like this. What's the flow structure changing? Like the vorticity. You see the maximum vorticity in the increasing. Okay, if you see this one, the first vorticity is increasing. That means when we're changing the circular cylinder from square, when changing the cylinder from square to circular, the maximum magnitude of vorticity is increasing. Okay, that means oil getting stronger. This is the streamline. Okay, streamline. Right? This is what we call the recirculation bubble. That means the flow is recirculating. Okay, this is the recirculation bubble line. What changes here? You see the flow is separated for this configuration R over R0 square cylinder. But for other cases, like it is reattached, separation at the trading. Okay, for this case, like here. Then what happens? This bubble size. This bubble size getting smaller. This is the longer, then getting smaller the surface. So the bubble length is changing. What is the connection between the bubble length? Why are you investigating the bubble length? If bubble length is closer, you will have higher heat transfer. Okay, stronger recirculation. That means higher heat transfer from the cylinder. This is now the time in drag force, drag coefficient or drag force. Okay, that is streamline force, and fluctuating drag coefficient means the oscillating drag coefficient. Okay, another is the fluctuating lift coefficient, means oscillating lift coefficient, the force coefficient in the wires. How it changes? You see here, when we're changing R to 0 to 1, like square to circular, you see the minimum drag happens at 0.5. Right? So if you consider the wind force on the structure, which configuration you will choose? You will choose minimum force R over 0.5, means this one. Right? But the fluctuating forces, this one and this one, it is 0.25. That means if you consider both fluctuating forces and binding forces, then this is the good configuration. You have to make the corner rounded at 0.2, between 0.25 and 0.5. That is why in the recent building structure, you will find rounded corner instead of square corner. Okay, in most of the modern buildings, higher filling, you will find rounded points. Okay, this is for the wind force. And if you see the Nusselt number, means the heat transfer. Okay, if you see the heat transfer, then the maximum heat transfer is for the circular cylinder. When R1.1, maximum heat transfer. Nusselt number. That means in the case of stream by flow, when this is the alpha intercept, okay, the flow is from this to this. Then you have to make your like capacitor or the components on the board circular is better. Circular shape will have higher heat transfer, right? Then this is previously it was okay. Now we change the alpha from 0 to 45 degree. Then let's see what happens. When we're changing the alpha, this horizontal axis, the vertical axis is R1. We found 4 different flow patterns. Okay, one is this is the forward flow. We have a primary discharge bubble on the sides. And the pattern B is like this. Flow separates from one leading corner and one trailing corner. And pattern C is very interesting. We have secondary recirculation bubble, the trailing edge. And for pattern D, we'll have the trailing edge separation. If you see the flow pattern, you are right, but you can say which pattern has higher heat transfer. You see, here we have the recirculation bubble is very close to the surface, right? That means we can understand this flow pattern has higher heat transfer. Okay, higher heat transfer and lower heat transfer, it is connected to the flow pattern. Okay, so we expect we'll see in later that this pattern has higher. What are they? Here are the details of pattern A and B. This is the pattern A, pattern B, pattern C, and pattern D. If we run into here, here are the flow patterns for the 4 cases. You see here the recirculation bubble is very small. It goes to the base. Okay, now see the process. This is again the timing drag. Horizontal axis is the alpha. This is CL bar means time inlet, time fluctuating drag, and fluctuating rate. If you consider the process, the minimum drag is alpha 0.5. That means if you just slightly rotate the cylinder 5 degree, then it will have minimum process. Okay? For both fluctuating and also the timing. Now see here. These are the process. All cases, we have minimum drag force when R over R is here. Okay, alpha about 5 degree, but R over R like 0.7, like 0.756, something like that. That's the minimum. If you consider the Nusselt number heat transfer, we see now here at alpha 45 degree in pattern C, we have heat transfer. Pattern C, you remember pattern C, this one. Okay, you have to rotate the cylinder 90 degree. And R1 should be 0.25. Okay, that's minimum heat. So these are the sketch of the flow pattern. When we're changing from pattern A to pattern B, we have increase in heat transfer. Okay, when we're changing from pattern B to C, again we have increase in heat transfer. Again, pattern B to C, we have the highest transfer. This is the optimum cases for heat transfer. It's good configuration for the heat transfer. Now, effect of R over R and Reynolds number. Now we are changing R over R and Reynolds number flow velocity. Then let's see what happened. Then again we found 4 flow patterns. Okay, pattern A is steady flow. Steady flow. There is no carbon velocity. Okay, at Reynolds number below like 48. And in pattern B, we call it trailing edge separated flow. That means flow separates from the trailing edge. Okay. And pattern C is the leading edge separation flow. Flow separates from the leading edge. Okay. And pattern D, we have the leading edge separated flow. That means flow separates from the leading edge. Okay. So here we found the flow. Again, we'll see which flow pattern has higher heat transfer or which flow pattern has the smallest wind loads. This is the transition between steady and unsteady flow. Okay, at Reynolds number 49, there is a steady flow. Okay, and at 50, there is an unsteady flow. Okay, that's the boundary that gives the boundary between steady and unsteady flow. The Reynolds number changes like this. Okay, this Reynolds number. If we have higher R over R, then we have smaller critical Reynolds number corresponding to the transition from steady to unsteady. Now we have the CD. CD, if we increase the Reynolds number, draft force is decreasing. Okay, draft force is decreasing. But if we increase the Reynolds number, this flat-fitting forces all are increasing. Draft force is increasing, but flat-fitting forces are increasing. If we consider the Nusselt number, then we see when we increase the Reynolds number, they all are increasing. They all are increasing. But what we see for the case of R over R, you see the maximum heat transfer is at the right corner. That corner means higher Reynolds number and higher R over R. That means this circular cylinder is the best configuration for heat transfer. This is the separation point changing. I think you will not be interested on this because it's explain the physics of flow. Now, if we see the dependence of U max and delta, delta is the boundary layer displacement thickness. You may or know or not. No, this is the boundary layer. That means how the shear layer is close to the side surface, or how far. And this U max is the how much is the flow velocity on the shear, how big. This is the quantum. And why for investigation? So this is connected to the heat transfer. If you have U max, you have high heat transfer. See, we have high U max. Here we found high heat transfer, right? And if you have a smaller tail stir displacement thickness, then you will have higher heat transfer. Smaller displacement thickness means the flow is close to the cylinder. Okay. So this explains actually the correspondence between the flow and heat transfer forces. This is the normal example. We did empirical relationship between the boundary layer displacement thickness and R over R and Reynolds number. Then we come to the conclusion. First effect of R over R. We found CD is minimum at R over R 0.5 and flat-fitting forces are minimum at R over R 0.25 due to the postponement of flow separation to the trailing corners. Heat transfer is maximum at R over R1, that is 33% higher than R over R. So if your heat transfer is important, you should choose surface. Okay. And for the effect of R over R, forces are strongly sensitive to R over R. The sensitiveness depends with decreasing R over R. So what is here is the minimum force at R alpha equals 5 dB and R bar are 0.74. That means if you consider the force like building structure, you should choose this shape. Alpha should be about 5 dB and R bar rounded corner like this. Minimum heat transfer. This is for the heat transfer. That means E square shape is worse, very flat for the heat transfer. On the other hand, the maximum heat transfer, if you increase the alpha, if you choose the square cylinder, square shape, but the alpha should be 45 degrees. It's close to the square, but there should be slightly rounded corner, 0.25, not the structure. Okay, so this configuration is the best configuration for heat transfer. Maximum heat transfer is 45.7% and minimum. That means if you choose the square cylinder and if you choose this configuration, you will have 37% higher heat transfer. That is quite huge. And the effect of R on 4 different kinds of flow states, okay, in the domain of Reynolds number. What we found, flat-field process goes with Reynolds number, okay, and heat transfer enhances with R bar R Reynolds. That means if you increase the R bar R, or if you increase the flow velocity, there will be higher heat transfer. Thank you very much.
Thank you very much for your excellent speech. Following, let's welcome Professor Xiaogang.